What do you do when you discover audible artifacts, clicks and dropouts in your digital audio system? And how do you solve the problem if your signal path is not optimal and clean? You will only be able to solve these issues with the right knowledge and the right techniques, and that is what I'm going to show you in this episode. And look out for the tips and answers in the end of the video. Hi, I'm Christian and you're watching the TC Universe series. Being in control of clock jitter is a big part of a clean audio path, and it's only becoming more relevant as time goes. In this episode, I'll take a deep technological look into jitter. I'll show you how it originates, I'll show you how it finds its way to affect audio itself, and I'll show you how to eliminate it with Clarity X. So let's look into it. In synchronous digital audio systems, all devices operate on a specific and common clock rate. For TV and film, it's 48 kHz. This clock can be more or less stable on a short-term basis, while on average being exactly the correct rate. This short-term timing instability is called jitter. Jitter comes for a number of reasons. It could be noise or hum induced on digital audio cables, just like you know it from analog cables. Or it could be long cables with limited bandwidth, rounding off the electrical signal edges. There are also a lot of bad clock designs inside products on the market. These circuits could have significant self-noise and add gain to incoming jitter. In MADI and audio networks like Dante, AVB and AES67, audio packages are transmitted in discrete time slots. Due to the available time slots, these networks have built-in jitter, and therefore they pose a both bigger and increasing challenge. Jitter can affect a digital audio connection, for example AES3, and break the chain, resulting in audio clicks and mutes. But jitter will also find its way and degrade audio itself via A to D and D to A converters. Consider the clock from earlier. The audio clock is used for setting the timing of the converters, and ideally a D to A converted sign would look like this. With jitter on the clock, the same digital sign would be DA converted to something like this, and in a real setup, this modulation may be audible. The higher level and higher frequency the audio has, the more sensitive it is to jitter on the audio clock. Therefore, a full-scale, high-frequency audio tone is often used to examine to what extent a converter is affected by clock jitter. Clarity X holds a highly refined version of the TC-developed JetPLL technology. This circuit sits between the digital inputs and the DA converter and the digital outputs. It is basically stopping all incoming jitter from ending up at the DA converter and the digital outputs by acting as a really efficient low-pass filter. Let's examine how jitter will affect a D to A converter. I will use a 10 kHz -1 dBFS sine with extremely low phase noise. In this first example, I'm using a standard DA converter without jitter rejection, but also without any jitter applied to the incoming signal. As you can see on the frequency spectrum, this looks quite ideal converting the 10 kHz tone. The noise floor looks rather clean. Now look what happens when I apply a fairly normal jitter level to the digital inputs on the D to A converter. You see the noise floor rises because the white jitter noise modulates onto the 10 kHz audio tone. If I then apply a sine jitter level of say 80 nanoseconds, which is not too far from what is inherent in a MADI or audio network stream, this is what we will get. As you see, this is quite non-musical and now a real problem. Then let's do the same with Clarity X. First the 4 nanoseconds white noise jitter, and you see no artifacts. Then we can try the 80 nanoseconds sine jitter. We can verify that the 1 kHz jitter is reduced by at least 85 dB as the low-pass filter described, and that there are no jitter artifact left in general. So what the JetPLL in Clarity X does for me is to make sure I don't have to worry about the jitter level in my monitoring system. Clarity X features a highly advanced freewheeling clock mode. If the external sync is lost, Clarity X will continue on a 96-bit precise version of the last good sample rate. This way, disturbances of your digital speakers are minimized despite potential sync instabilities and project recalls. Another benefit is that even with lost sync, your monitoring system keeps running with a minimum set of input sample slips. This makes me feel very safe in a live mixing situation. And now I'll answer questions from you. How do you set your clocking for your studio in order to have the best audio performance? That question has been discussed over and over again. And as a rule of thumb, you should set the primary converter to be the clock master, because it's the easiest clock circuit to design well. This means that in a recording situation, I would set my A to D converter to be the clock master, and in a mixing or mastering situation, I would set the D to A converter to be the clock master. But with Clarity X, you get jitter rejection to a level where there's basically no difference between internal and external sync. So now you don't have to worry about your monitoring system, but only about your recording path. Look out for more pro videos in the TC Universe series.